Hello everyone, and welcome to this session on optimization of steel structure with STAAD. I am Surajit Ghosh, and today I'll cover how we can use different optimization technique available in STAAD to select most economic section for any structure and reduce material usage as well as overall cost of the project. Optimization is quite different from the traditional member design approach. So in this session, I'll start with the basic concept of optimization and why it is required. I'll cover few case studies to discuss how and in what extent optimization can help to achieve a better design result. Optimization is not a single step approach. Rather, multiple iterations are required to find most economic section. For better outcome, we need to refine those iterations using some additional design parameter and comment. I'll discuss those comments, correct sequence, and additional parameter required during section selection. Finally, I'll cover how we can use only project-specific section during optimization using custom database, along with optimization of user-defined, built-up, or plate girder section. Let's start with some basic concept of steel optimization and why we should adopt this method for any steel design project. In traditional design approach, we create an analysis model in STAAD with proper dimension, considering only the structural element. There might be few non-structural element present in the structure, like a partition wall, or element which has less impact on analysis result, like sag rod. We don't consider those elements in the analysis model. Then a preliminary section is assigned along with specifications like member offset or release, support, gravity and lateral loads, and design parameters. On basis of these inputs, analysis is performed and those results are checked against section capacity during member design, which provides an idea whether the assigned section can withstand that load or not. After member design, pass-fail status is reported for each member along with critical clause and load. Consider this small warehouse type building with pitched roof. Standard I sections are used as column and rafter, channel section as purlin, and angle section as bracing. These sections are selected based on preliminary assessment, size of structure, column to column distance, applied load. Couple of gravity load and lateral load are applied from different direction, and combinations are generated based on table 4 of IS 800-2007 code. Required strength and deflection check parameters are assigned to the members. This structure is designed using Indian Steel Design Code IS 800-2007. Check code command is used in this model for member design. After design is performed, we can check the design results from post-processing mode, utilization table. Critical design ratio of each member is reported here, and we can easily notice that most of the members fail in design, with critical condition as bending interaction check. For some member, critical ratio is close to 1, whereas for few member, it is as high as 15, which clearly suggests that our initial section assignment is not correct and we need to change the assigned section. To find a suitable section, first we need to assess the region of failure. Accordingly, select a section which has higher capacity for that check. For example, if a member fails in bending or interaction, we need to increase the bending capacity. For that, we can move the flange apart from the neutral axis, which will increase the moment of inertia and section modulus. We can either increase the section depth or use a flange cover plate. If a member fails in shear, we can increase the web thickness or strengthen the web against shear buckling by adding some intermediate stiffener. These are just few examples. There might be several other reasons of failure, and based on the failure criteria, we need to select a section with higher capacity. This table doesn't provide a clear idea why the section fails. For more details, we can use track to parameter and check detailed design result reported in the output file. All intermediate value, critical ratio for each design check is reported here. This entire design process with check code command is manual. We are designing the member based on preliminary section size, reviewing the design results and failure criteria, accordingly changing the sections. Then repeat this process again to find whether the modified section is adequate or not. We need to repeat this process manually until a suitable section is achieved. Check code command performs a single-step member design and reports whether a member pass or fail for the applied load and design condition. No suggestion is provided to clarify what is required or which section is adequate. There is another problem of this tedious manual approach: changing the section size if it is not utilized properly. Consider the STAAD model. Similar structure, but this model has multiple levels. Applied loads are also different. If we review the design result from the post-processing mode, we can notice that few members fail in design, like this column I section or this tube section used as rafter. We need to increase the section size. Also, there are few members with very small design ratio, like this girder section. Ratio 0.2 means only 20% capacity of this section is utilized. We can easily reduce this section size and select a section which is properly utilized. Once again, we need to go for manual iteration to find an optimum section size. As a designer, our goal is to select a section which is most economic, utilized properly, and which can withstand all loads without failure. With check code command, we can achieve that, but lot of manual trial and error is required to find this optimum section. If we consider a large plant or pipe rack structure with thousands of members, it is quite challenging and time consuming to optimize the structure manually. Unless we use an optimum section, material usage will be in the higher side. For example, I have compared total steel usage of this model before and after optimization. We can easily notice a considerable reduction of overall steel usage when we optimize the structure and use sections which are more economic. That's all about traditional design approach and how we can optimize a steel structure manually using multiple trial and error. We can automate this optimization process in STAAD and select an economic section without any manual iteration using select or select optimized command available in the design command window. Though both these commands optimize steel section, design approach is slightly different. I'll start with select command, how it performs optimization in any STAAD model, and how to use it properly. Similar to check code, select command also designs a member, but it does so iteratively. For select command, program first performs member design on basis of applied load, assigned section and design parameter. This is exactly like the check code command. But the design process doesn't end here. In the next step, program reviews the utilization ratio. Either it is greater or less than 1. If it is greater than the allowable ratio or the member design fails in design check, say ratio is 1.2, then program selects the next heavier section available in that section table, maintaining the original shape and type of section. If the assigned section is from Indian database S-shape table, new section is selected from the same table. Section from another database is not considered during selection process. Another I section from Jindal database is not considered if the original section is from Indian database. There is a way to consider section from other database. I'll cover this later. Also, section type is not modified. Channel or angle section is not replaced with an I section. After selecting the next heavier section, program performs member design again with that modified section. If this new section also fails, it selects another higher section of that type. If the utilization ratio falls under 1, like 0.7 or 0.8, it indicates the section is not utilized properly. Capacity is higher than the demand. In such case, when critical ratio is less than 1 during section selection process, program reduces the section size, selects a light section from the database, and redesign to find the modified ratio. This whole process, design a member, review the ratio, accordingly select another section and redesign, continues till the ratio is close to 1 or any specific ratio value. Few iterations might be required to complete the design process and find most economic section for a member. There are two outcomes of this iterative design approach. Either an optimum section is selected which has demand versus capacity ratio close to 1. In such case, program terminates the design process and reports that as optimum section for that member. Also, it might happen, though the largest section from the database is selected, member fails in design. As there is no higher section available in that database, design process stops here. Failure condition and last section used for design is reported for that member. In such case, we can manually change the shape or database, even go for a built-up section with higher capacity. Consider this model. After non-iterative member design with check code, few members fail. For few members, critical design ratio is very small. Using select command, we can find what is the optimum section for each member. For that, from the still design page, remove this check code command, replace it with select command, and assign it to relevant members. We can perform section selection based on strength design criteria by defining design parameter for strength check only, or we can combine both strength and serviceability criteria under a single design block and use it for optimization. In such case, program selects a section considering both strength and deflection check results. Critical most ratio governs the section selection. Here, I have defined both strength design and deflection check parameters under a single design block to consider combined design check, and used load list envelope command with proper envelope number. Separate envelope for strength and serviceability condition are already defined. During analysis, a warning is reported. It suggests to go for reanalysis as iterative member design is performed. This warning is very important, and without reanalysis, design result might be incorrect. For now, let's ignore this warning and proceed for design. As iterative member design is performed, it takes slightly longer duration to complete the design. We can review the utilization ratio from post-processing mode. This time, two different sections are reported for each member. First one is the assigned section, which is used for analysis and section force calculation. Second one is the optimum section computed after iterative section selection process. This section was not considered during analysis. All design ratio values are now close to 0.9, which is the allowable design ratio. We can compare these results with the previous instance. For example, design ratio of member 25 was 0.2. Now it is 0.8 and suggested section is ISWB 175, which is the most economic section for this member. Similarly, few members were failing like member 1 and 6. Now these members pass with ISHB section. Ratio is close to 0.8. Program internally performs an iterative member design. Each member is designed multiple times with modified section to find most economic section. That section is suggested here along with the critical ratio. With this iterative member design approach, we don't have to perform any manual trial and error. program selects the optimum section after few iterations, which is more accurate. Though this seems okay, there are few problems with this result. During optimization, section size is modified, so stiffness at different part of the structure is also changed, which affects the load path and force distribution. Instead, stiffness method is followed to analyze any structure and compute section force. When the assigned section of a member is modified, there is a change in stiffness as inertia value is different, due to which load distribution is also changed. Heavy section attracts more force compared to light section. Consider this simple goalpost frame where I have applied a UDL on the beam. This structure is symmetric with same column section. If we review the section force, all values are identical for these two columns as load is equally distributed. In the next model, I have assigned a higher section to one column and light section to another column. Now we can notice, though the load and other structural conditions are symmetric, still column with heavier section is subjected to more force compared to the weaker section. This indicates that after section change, member is subjected to different force, but during optimization with select command, initial member force is considered throughout the process. For member 1, if program selects a section with bending capacity 20 kN, it is sufficient for the initial member force as the demand is 19 kN. But after this section change, demand is increased to 26 kN. Capacity remains same, 20 kN. Selected optimum section is not sufficient to handle this extra force. It will fail. So, it is important to reanalyze the structure after optimization to calculate modified force and check whether the suggested optimum section can withstand that modified force or not. For this, every select command must be followed by a performance analysis command. This is also suggested in that warning. Then we need to add a check code command to verify if the optimum section passed the design check with modified section force. This is the correct sequence for optimization. Let's take an example. In this model, most of the members fail when we perform design using check code command. For some members, critical ratio is as high as 15, like member 6 or 7. After optimization with select command, most of these members pass with ratio close to 1. For member 6, section depth is modified from 250 mm to 450 mm. Ratio is reduced to 0.9 from 15. For member 7, it is exactly 1. Few members are still failing. I'll handle those later. There is a way to achieve optimum results quickly. These sections are selected based on initial section force, which might be different due to section size change. Let's find out whether this section can handle that modified force. After section selection, we want to reanalyze the structure. From input editor, we can add required commands. Add performance analysis command after select, followed by a new parameter set. Design code remains same, IS 800-2007 LST code for this model. Optimization process is same for every design code. We are going to use all design parameter specified in the earlier block. Unless we change any of these values manually, design parameters are carry forwarded to the new design block. Finally, add check code command to design the optimum section with modified force. After design, we can review the utilization ratio. This time, several Raptor and Purlin member fail, which were passing earlier with ratio close to 0.9. For example, member 2. Previous ratio was 0.95, which has been changed. Same for member 32 or 33, where ratio is changed from 0.9 to greater than 1. This is expected due to increased member force. Previously, demand was very close to section capacity. 0.95 or 0.98, a slight change in design force will increase this value. So these sections are not safe, and after first section selection, we are unable to find optimum section for several members. In such case, we need to perform multiphase optimization. Repeat the optimization process again using a second select and deanalysis command after the first set of member selection. In the first optimization process, an economic section is selected, and on basis of that, analysis results are recalculated. In second stage of optimization, these modified analysis results are used to select an optimum section once again. If any member fails after first stage due to increased force, that section will be replaced with a suitable section. Then we will analyze the structure and go for final design using check code command. We can increase the level of optimization with multiple select command. To perform two-stage optimization in this model, we can add required commands from the input editor, copy the select and analysis command, paste it once again, modify the parameter block number. With this, we are performing two-stage optimization followed by final design check. This method decreases the chance of section failure after final selection. If we check the design result, we can notice member 2, 32 passed the design check now, and assigned section is different from the previous case. During second optimization, program selects a higher section considering modified force value. By performing multiphase optimization, design results are now more accurate and sections are more economic. There are still few fail members, few purlin and bracing. For these members, critical ratio is close to 1. If we go for another level of optimization with another select command, this member might pass, but it is not always recommended to use multiple select command in a model due to higher runtime. When we perform an iterative section selection process, program takes longer duration to complete the design than non-iterative method. For each member, program performs design, reviews the result, changes the section size, then repeats these steps until the optimum section is selected. Multiple select command further increase the overall analysis time. I have compared analysis time of this STAAD model, and the time difference of one stage and two stage optimization is around 30 seconds. For a large model with thousands of members and load case, the time difference will be high. So we need to select the level of optimization carefully. We can start with single phase optimization and review the results. If there are plenty of failed members, then go for second stage or multiphase optimization. There is an alternate way to convert this optimization process quickly. Consider these members which fail after two-stage optimization. During optimization, program selects a section with ratio close to 1. If the critical moment is 100 kN, program selects a section with bending capacity around 100 to 105. There is almost negligible reserve capacity. So, chance of failure of this optimum section is quite high. If a section with slightly higher capacity is selected during optimization, we can avoid this failure. That we can achieve using ratio parameter. Using this, we can inform program to select a section with higher capacity. Ratio is the critical force by section capacity value. By default, it is 1. If we specify the ratio as 0.8, program compares the critical force against 80% section capacity. We can consider this during section selection. Specify a ratio parameter as 0.9, which will limit the maximum capacity as 90% of the section capacity value, and instruct STAAD to select a section with 10% reserve strength. For this example, with ratio 0.9, program will select a section with capacity more than 110 kN, Any section with capacity less than this will be rejected. So, selected optimum section has some reserve capacity, which will help in the next design check if section force is increased. Basically, we are forcing the program to select a section with higher capacity, considering the uncertainty of critical force. In this STAAD model, we can define ratio parameter before the first select command, consider maximum 80% capacity during section selection, plenty of reserve capacity for the initial phase. In the second stage of optimization, we can reduce this reserve capacity by 10% with ratio 0.9. During second stage, most of the sections are already optimized. Still, we can consider some reserve capacity to handle extra force. Finally, before the check code command, we can set this ratio to 1. This time, we are interested to know whether the optimized section pass or fail. With this variable ratio parameter, we are forcing program to select a higher section at the initial stage and fine-tune that section during final stage. This will converge the optimization process quickly, and after a couple of stages, we can expect an optimum section without any failure. There are still few failed members which we are going to rectify in the next step. If we review the design result, we can notice one problem. Consider this first panel with column and rafter member. Program suggests different section for different rafter member. STAAD performs analytical member design where each segment is treated as a separate member. During optimization, program selects optimum section based on the critical member force of each rafter member, which results variable section throughout the length. In reality, we use uniform section as rafter, or if the variation is higher, we use taper section. Another common example is the top or bottom chord member of a truss. STAAD has no idea these are part of a single member and suggests different section. After optimization, we can assign same section to all these members using an additional command, group. Purpose of this group command is to assign the highest section among all assigned member to every member present in that group. We need to assign this command after the select command. After optimization, program will suggest different section for different member. If the section size varies from 250 to 450 for a rafter, then section with 450 mm depth is assigned to all the rafter members. We can group the sections based on property value. Either we can consider highest cross-sectional area AX for grouping, or use section modulus about major or minor axis. Normally, we use this AX option and assign the section with highest cross-section area to all the members. In this model, I'll specify this group command after the first select command. We can use this after current option, then assign this to the left rafter members. We need to repeat this to the right rafter, left and right column. Each rafter and column member must be specified under a separate group. If we want to use same section throughout the structure, then we can assign all rafter under one group, though this produces uneconomic result. Force might vary between different parts of the structure, and highest section is assigned to all rafter member. Unnecessarily, we will use heavier section where force is significantly small. What I recommend, first group and review the rafter section for each bay separately. If the sections are close, we can use same section. I have created 4 separate groups for this bay. These groups are linked with this select command only. It is not carry forwarded to the next select command. Program discards this information after grouping. We need to specify these groups after each select command. Either repeat this process or copy paste the data after next select command. There is an easier way to retain this group information. We can use another command, fixed group. we need to define it once in the model, before the first group comment. Purpose of this command is to retain the group information in the memory and use that information for all select commands. If we perform multiphase optimization, after each section selection, program groups the members and this group information is considered from the first block. To summarize, correct sequence with select and group command is: first, specify all design parameters along with ratio 0.8, then assign select and fixed group, followed by the group command. Next, reanalyze the structure, change the ratio to 0.9, perform another set of optimization and reanalyze, then change the ratio to 1, perform redesign using checkcode command. In this whole process, design parameters are constant, considered from the first block, except the ratio parameter, which we are changing in each block. This is the correct sequence for optimization and grouping of members. After optimization, same section is now assigned to all rafter and column members, which is the highest in each group. Due to this, few members have smaller utilization ratio. After optimization, program selects an optimum section for these members, but it is replaced with a higher section which reduces the ratio. One thing to notice, two different sections are used for rafter member, 500 depth for left rafter and 600 depth for right. In reality, we assign same section for both sides. As we have created two separate groups for the rafter, program selects individual highest section for each rafter. To select a single section for all these members, we can merge these two groups or define a single group considering all rafter members. This time during optimization, program will select optimum section for individual analytical member. After section selection, program will assign the highest section to all rafter members. This will ensure a uniform profile throughout the length of rafter. Using same logic, we can further create a group with all rafter present in this model, which will assign the highest selected section to all rafter, though it can be unrealistic sometime. All these optimum sections are added in the property table. These are selected by the program during optimization process, but not yet assigned to any member. Original sections are still used. If we are satisfied with the result, we can replace the assigned section with the optimum section. From the post-processing mode utilization ratio table, we can review the results first, then use this update properties tab to replace the old section. This is an irreversible process. Now, if we review the properties table, we can notice that all member properties are updated with the new section information. That's all about still section optimization in STAAD with select, group and fixed group command. There is another command available for section optimization, select optimized. It is similar to select. There is only one difference. It performs two-stage optimization. For select optimized, program first performs a non-iterative design using checkcode command and reviews the design ratio. Next, optimum section is determined using select command. After the section selection, program reanalyzes the structure. This is same as select plus perform analysis command that we have used till now. But in this case, we don't have to provide the reanalysis command manually. It is within the select optimized routine. And not only that, after the analysis, based on the modified section force, program once again selects the optimum section using another select command. Basically, select optimized is a two-stage section selection routine with multiple select and one reanalysis command. If we use this command, optimum section is reported after two optimization cycles. Still, we need to check whether the modified section is adequate to withstand new section forces. So additional analysis command followed by check code command must be specified after select optimized command. This is an example how we can replace those select, group and fixed group command with select optimized command. Though it seems simpler to define, I don't prefer to use this command as we can't control the section selection with intermediate ratio value. We can only specify a ratio before the optimized command, which is used for both phase. This might lead to longer optimization cycle and failed member. I prefer multi-phase select command rather than select optimized, as that provides better control over section selection with intermediate ratio value and number of cycles as per requirement. During optimization, program selects same type of section from same database based on the original section information. If we use an ISMB 250 section from Indian database, program will select an optimum section from this database including ISLB or ISWB section. Same for channel or holo section. Sometimes all these sections are not available in the market, or we don't want to use specific type of section in the project. Say we want to use only ISMB section, not ISHB or ISWB section. To ignore these sections during section selection, we can use a design parameter, profile. Using this parameter, we can inform STAAD to select few specific shapes for optimization and neglect rest of the shapes present in the section library. Inputs of profile parameter varies from code to code. For IS800 code, we can use ISMB, ISMC or IW shapes, whereas for AISC code, W, M, S shapes are available. We can assign more than one profile to a member, like we can use ISMB and ISWB profiles and assign this to the column member. This parameter should be specified before the select command. After design, program will suggest only ISMB or ISWB section. Rest of the shapes are ignored. Using this, we can control the section during optimization. There are two other design parameters which control section selection, dmax and dmin. Using these two parameters, we can specify maximum and minimum depth of section which can be selected during optimization. There are several conditions when we can't increase the section depth, like height limitation. For example, any section with depth greater than 500 mm is not allowed, which we can specify using dmax parameter and assign it to relevant member. During selection, if a section with depth more than 500 mm is selected, program terminates the process and report the member as failed with last used section. Using these parameters, we can use specific profile or restrict the section depth. But there are other conditions when these parameters are not sufficient. It might happen that all sections of that profile are not available, like ISMB 250 and 300 are not available. Or we want to use few specific sections from that database. Basically, we need a subset of original database for optimization. During section selection, if program finds the heaviest section in that database is not sufficient, it reports a design failure. There might be some heavier section available in other database, like in Jindal or Tata database, but those are not used as change of database is not allowed. To use specific section or section from different database for optimization, we can create a custom database with all available sections, including section from different database, and assign any section from that database. During optimization, program considers that custom database and selects any section from that list. In STAAD.Pro 2023, two different databases are available. Standard is a new database with few countries only, and legacy is the old database. I'll use this old database for customization. We can open the section database manager. All available databases are listed here. and we can open the required database from the tree. Check and edit any section, even add a new section. I don't recommend tempering this default section database as it might cause some problem in the future. Rather, we can create a copy of any database, import that in STAAD, then customize it as per requirement. Even we can import sections from Excel or CSV file. In the program data folder, all these default databases are available like Indian database or Jindal database. We can create a copy of any database, open using SQLite software like DB browser, customize, then import that in STAAD, or customize it after importing. I am not going to cover this process in detail. It requires some time. I have published few videos on this topic. You can check those for more details. I have already created a custom database and imported that in STAAD, specific ISMB and ISHB section. Few parallel flange sections from Jindal database are available here. We can assign any section from this library, like an ISMB 250 section. During optimization, program will select a section from this custom database as the optimum section. Now, a NPP section along with ISWB or ISHB section is suggested as optimum section. With original database, only ISMB or ISHB sections were recommended as optimum section. Using this custom database, we can find the most economic section considering sections from different database. It is not limited to a single library. Not only that, we can add any custom user-defined section directly in that database with similar type of name. Like I have included ISMB 800 section here. This section is also used for optimization. Finally, I want to discuss how we can use multiple user-defined section for optimization. Use of built-up section in a still structure is quite common, which we can create from user table or section widget. Also, we can add this section in standard library. We can optimize any user table section except general, prismatic and iSection type. There are few additional rules, like multiple sections must be present in a user table for selection. Optimization is limited to a single table. Selection of section considering different table is not possible. We can create a user table with any type like a wide flange section. Define multiple sections with variable property under that table and use it for optimization. In this model, I have created a wide flange user table and specified 5 sections with different dimension and property. I want to know which section is most economic for few members. We can assign any of this section and perform optimization. During selection, program performs iterative design considering each of these sections and selects most economic section available in the user table. Though I have assigned same section to all these members, different section from this user table is suggested to different member. For built-up section, rather than assigning a specific section to a member, we can create a user table with multiple sections, perform optimization, and program will inform us the optimum section from that table. If there are multiple tables, then each table is used separately for selection. Using this approach, we can even add standard sections from different database as a user-defined section and use it for optimization. I have developed a custom Excel file where I and Holo section from different databases are available. Sections from Indian, Jindal and Tata database are available here. I can select any section from any database and add it in STAAD as a user table section. Say I want to use ISMB 200, 300, 400 and 500 along with NPB section from Jindal database with depth 300, 400 and 500. After selection, Simply click on this tab to add the selected sections in STAAD. An OpenSTAAD code is running in the background, which will instantly create a user table with white flange type and add all these sections with a custom name. This helps us to identify the section in future. I have already discussed such automation technique in my previous series on automation with STAAD. In this STAAD model, a user table is created where all these sections are added with a custom name, with properties considered from standard database. We can now use this table for assignment and optimization purpose. With this approach, we can eliminate a custom database and use any section from any database for optimization. Even we can create a new built-up section and combine it with the standard section during optimization. If the highest section of database is not sufficient, built-up section will be used. That's all about how we can perform still optimization in STAAD with different command, parameter and custom database. With this approach, we can completely eliminate manual trial and error process and use optimum section with minimum still usage in any project. Before we use this optimum section, we need to review the results and check the feasibility and availability of the sections. Note that optimization is based on standard shapes. There are few conditions when we don't use a higher section, rather use a weaker section with customization like web stiffener or flange cover plate, even custom shape like cruciform or double eye section. Those are not considered during optimization. I hope this session will help you to select more optimum section in your project. Thanks for joining.